Hello everybody, welcome to a lecture on modeling with Basic Formal Ontology. I'm John Beverly, as you see. We're just going to get right into it. So first I'm going to motivate ontology engineering in general. I'm going to provide some motivation for BFO itself, Basic Formal Ontology, why you would use it, why we do. I'm going to talk about the theory behind Basic Formal Ontology, and then I'm going to walk you through a recipe for how you actually go about building ontologies with BFO. So getting into it. Why are we doing this? What's the background? Information silos. These are our boogeymen. They're repositories such like management systems, databases, etc., content of which can't be integrated with that of other information repositories using standard computing strategies. Now, these things are dangerous. It's well known silos get in the way of interoperability across data sets, across communication lines. As you can see here, one of the major projects that has been going on in the ontology engineering space has to do with organizing, coordinating information about narcotics, moving over the borders into the U.S. A lot of data pouring in every day. Not a lot of coordination, not a lot of insights that can be gleaned from the data that's being collected. It would be great if different groups that were collecting information about the same phenomena could integrate that information together and cover implicit information or new insights into how to, say, stop fentanyl or meth from coming into the country. But for many, many years, it has not been the case. There's been such coordination. Interoperability is kind of the goal we have in addressing information silos, but information silos at the end of the day are boogeymen, and they are dangerous and get in the way and cost lives. So these things are expensive too. 2020 report by NIST estimated the lack of interoperability across data sets cost companies between 21 and 43 billion. McKinsey estimates mid-sized companies spend about 20 to 50 million annually due to silos. That is a lot of money. I know we're in the States and we have a lot to give, but presumably that money could be spent better than it is. But you can see over here, this kind of big data pentagon, you can see kind of why these numbers are so high. There's a lot of high volume of data that comes in across devices, across the internet. Like your phone is generating a lot of data right now. Like anything you're wearing that's technological or hooked up to the cloud is as well. It comes in different formats, from different sources. Has inconsistencies, uncertainties, things that need to be reconciled. Data needs to be reconciled about the same individual, same area, same process over and over again, and it just accumulates at such a high speed. It's hard to keep up. It's hard to build software solutions that can keep up. And because of that altogether, if you look here on this, the far right on the bottom, this value piece to the big data problem is it's hard to extract useful information given these conditions from all the data that we have. So here's a great example. A sad example of how these things can go awry. Interoperability can go awry, and how silos can generate costly consequences. So, a while back, the Airbus, this manufacturing company for airplanes, they decided to have this kind of cross-European Airbus model A380. It was different parts of this plane were going to be manufactured in different European countries. They were going to work together, coordinate, and bring this together, much like Voltron, into a larger bot that folks can spend a great deal of money on flying transcontinentally. Unfortunately, there was some miscommunication with respect to how the wiring was supposed to be constructed. Maybe different units of measurement were used. It's not really clear. All that's known is that when the wiring was brought into contact with the chassis of the airplane and kind of run through the eye holes and whatnot to try to go up and down the plane to allow for electrical transmissions throughout the cabin. Turns out it was too short, that wiring was, and so there was some kind of miscommunication, failure to introduce interoperability or communication across these kind of different manufacturing endeavors. Ended up costing Airbus quite a bit of money and putting this project back by 2 years. These things are easy. These interoperability / information silos are easy to cause, easy to fall into, but again, also quite expensive. They're also everywhere. and it's important to see how we might address them. It kind of motivates a lot of the work that we do. But before I get into that, I do want to be clear about something. So when I'm talking about interoperability strategies, I'm talking about those strategies that mitigate or eliminate information silos, and it's important to get a little more careful about what interoperability means, because many people mean many things by interoperability. I've said it a couple of times already. You probably have an intuitive notion about interoperability, integrating data with other data, something like that. The problem is everybody has an intuition about it, and they're not all the same. So if cursory glance at the literature in Google Scholar on interoperability, it's easy to see that there are like at least 30 different definitions of interoperability, many of which are in, within the same domains. And so I'm not trying here, and I won't try to offer a new one. Instead, I want to kind of take a step back and think about different strategies for addressing interoperability across three axes: a machine-machine axis, a human-human axis, and a human-machine axis. And these are important to distinguish because they have different criteria for success. So on the machine-machine side, this involves addressing the more what you may have had in mind while I was discussing information silos across data streams or data sets or databases. This is how the machines interact with other machines. So it's associated strategies in this machine-machine interoperability camp often emphasize things like common metadata standards or business logic or APIs. The central conceit for our field, ontology engineering, is that any two heterogeneous information systems share some underlying formal structure that can ground machine-machine interoperability. On the other hand, there's human-human interoperability, and this involves addressing what we might call social silos, which undermine consistent communication across agents. And these strategies that fall into this camp often emphasize consensus-building exercises, dictionaries, evaluation of natural language, and so on. You get together in a meeting and you argue about the right way to use words. Underlying conceit here being that any two speakers of a given natural language share some underlying formal structure, whether it be grammar or otherwise, and that you can find some common ground. You can see this manifested in many ontology engineering circles. On the left, you'll see something for humans. This is a dictionary, DoD dictionary of military and associated terms, which is a snippet from there. This is for us. This is for the humans, to support human-human interoperability or communication, especially in times of war or military engagements in the U.S. Now, there's also the human-machine interoperability. This involves encoding human-human interoperability solutions into a machine-readable manner. This is how we bridge human-human and machine-machine. Associated strategies often emphasize things like data schemas or ontologies or knowledge graphs or standards for encoding these things. And we aim to encode our shared formal structures into machine-readable languages, and you'll hear that language. We're trying to make our insights or implicit information, our knowledge, machine-readable. And this is kind of the interoperability axis along which that encoding occurs. And you can see how that might manifest, right? Whereas previously I was showing you a dictionary for humans, now there's this mapping going on. At least that's what the arrows are supposed to signify. So there's some formal structure, like a taxonomy that you're seeing here, and this incidentally was done, but this is something encoded in a way that machines can read, reason over, use, and leverage in interoperability solutions. Now, the strategies, whether we're talking, I think many people over the years have talked about the axes in the way that I'm talking about them now, although not clearly distinguishing them. Still, it's not like I'm the first person thinking about this. It's not like I'm the first person thinking about interoperability or the first person thinking about strategies for how to address it. Of course not. The strategies are not new, although they are hard lessons for people to learn. Ontology engineering in general is aimed at addressing, in part, at least as one of its central pillars, these sorts of interoperability problems, and by introducing or creating formally well-defined, machine-interpretable, controlled vocabularies that represent entities and logical relationships among them. And what we do is we make explicit the implicit meanings buried in data by using basic principles of formal logic. And in doing so, we create a semantic layer that connects different database systems or information silos to one another because, remember, that central conceit, between any two heterogeneous data structures or data sets or databases, there is some common formalism, formal language, formal representation, We, as ontology engineers, seek that formal representation so we can feed it in a machine-readable way to the system software so that it can automate or check or integrate and do all that machine work that we love and we hope will happen someday. We're not the only people talking about this, and by we I mean people in academia. The Department of Homeland Security has been engaged in ontology research. They have it, as you see here, on a roadmap for 2024. They had ontologies represented directly in their AI outline. NGA hiring data stewards for ontologies. There's this project at the National Science Foundation in the States with building the prototype Open Knowledge Network, which is an ontology/knowledge graph effort to represent information across a vast number of domains and integrate it all into a central hub so that people can ask questions about things like, federal law as well as oil manufacturing documentation or something. You can federate, they say federate or cross-domain query and uncover new information. Again, not new, and this is just becoming more and more common. On Fox News just the other day, today's September 19th, 2005, on Fox News the other day, I heard a pundit say ontologies. First time I'd ever seen it. Somebody sent that to me, by the way. It was a very interesting talk. Look it up. Many groups have been looking at ontologies, have been leveraging ontologies, especially in the past couple of years, and been looking to hire new ontologists. This is a great time to get into the field, so great time to maybe listen to this. You see, I won't go through these, but just hop on LinkedIn if you're interested, if you want to verify. Again, hop on LinkedIn if you want to verify. Ontology jobs are in abundance. Now, okay, this is the background for ontology engineering. I'm going to be talking about basic formal ontology, which is a specific top-level ontology. I'm going to talk about some of the motivation behind it, why you would use it, why we use it. So certainly interoperability strategies support improved data quality better than others. Now, I've just been talking a bit about the kind of general motivation for ontology engineering being something like addressing information silos, creating interoperability strategies, whether it's human-machine, or machine-machine. There's another aspect to what we do. We don't just want to integrate data. It's not that challenging to make data interoperable. You throw a bunch of Python developers at two different data sets and have them stitch together some mapping. Like, if you got enough money, you can solve this. Not a big deal. You have to update it. Versioning becomes an issue, but versioning's a problem for everybody, right? Like you can still do it. But some strategies for solving interoperability are better than others at allowing you to leverage technology that already exists or write scripts or code that can help you improve data quality. And at the end of the day, for me at least, ontology engineering is not just about interoperability. It's about interoperability with an eye towards improving data quality. I want the data to be better. We all know data's bad. We all know it's not high quality. Like, where is it? Tell me where the high quality data is. How do we improve it? Are we going to do it manually? Absolutely not. Are we going to leverage machines to do it? Absolutely. How do we do it? Well, we need to back up and think about how we're integrating our data and what tools we can use to leverage, how we can set ourselves up in the future so that we can automate as much as possible the improvement of data quality. That's sort of what we do as ontology engineers. Those are the two central pillars: interoperability and data quality improvement. BFO, Basic Formal Ontology, is a top-level ontology, super high level. These things that you're seeing on your screen, that represent classes that should seem, some of them which should seem rather odd, some of which should seem somewhat commonsensical just based on the label, but it's supposed to be incredibly high-level representations of anything that could exist in the world. And there's logical structure built into these relationships that allows you to populate logic downwards and create that semantic layer using basic principles of logic on data sets across the world, across domains. And it's been quite popular. It is the first ISO standard for top-level ontologies, IEC 21838 or ISO IEC 21832. It is a DoD Enterprise Standard baseline. It is a JESIC technical working group baseline. It is mandated for use across the DoD and the IC communities alongside one of its extensions, Common Core Ontologies. Again, quite popular. It's used by over 700 projects and counting worldwide. Barry Smith and I keep a tab on this. We update the user page you can see here with links to all these projects that are going on. It is, I can say without question, the most widely used top-level ontology in the world. And it's based on these methodological convictions: realism, hub and spoke, fallibilism, and adequatism. I'm going to walk through these so you can understand the background, like what is it that we're doing and why. And these principles, these here, I will argue, are the best, are these convictions are the best convictions that support both interoperability and data quality improvement. So realism. BFO is designed to represent the world rather than just concepts or ideas about the world. Look, ontologies are specifications of fundamental structure of the world. I think that's my line as far as realism is concerned. We're looking for that basic logic that connects data, right? And so that's some kind of fundamental structure. There's something out there that's uniting, bridging logically data or heterogeneous data sets otherwise. I think this view encompasses other positions on ontology engineering circles that go under the heading conceptualism and pragmatism. Conceptualism is a view that ontology should be modeling concepts, like what we think about the world, and the way the world is a different question, right? But we know, like, we can hold certain that we are modeling what we think about the world, at least, and that's different from the world itself, and so there's an epistemic gap. On the other hand, pragmatism is ontologies are modeling whatever you need them to model, right? And so I think realism, as I've characterized here, actually encompasses both of these. So it is, the concepts in the world are real. So there is some fundamental structure representing them and the relationship of concepts to the world. So there's that. And pragmatism, whatever we want to model, that is also real. So I think realism is the bigger boat. And to me, realism allows us to have something of, at least aim for having something of an external arbiter to our decision making, our modeling choices. Because it's not just me trying to model my concepts. It's not just you trying to model what you want to do. It's us trying to do that while respecting, at least practically speaking, how the world is independently of what we think. And part of this is motivated by the fact, just observation over many years, if we attempt to go from the words we use, or the concepts we use, or our desires, to modeling the world, it's very unlikely that we're going to end up in the same place. You and I, if we're modeling just the concepts or the words that we use independently, it's unlikely that we will wind up modeling the world in the same way. On the other hand, if we both aim to model the world itself and map our words to it, it's much more likely that you and I will remain coordinated. The world is our external arbiter, and we can see it, and we can feel it, we can touch it. And our words, we know, are ours, and we hope they map up to the world, and we try. But I think this shift in thinking, I'm not just trying to model what I think, I'm trying to map something out there that others would agree to. That's a different beast. It's much more likely that we'll wind up in the same place with that kind of mentality, at least I find in practice. Hub and spoke is also a cornerstone of BFO modeling. And this is just basic software development principles. This is modularism and extensions. And so, but it's born out of early days in '98, the development of a central hub to organize a great deal of data that emerged out of the Human Genome Project. And you see here the mission, the gene ontology, is sort of like an opening salvo in the communities. Gene ontology is probably the most successful ontology that's ever existed. Billions of dollars have been used to fund it, maps all sorts of phenomena in the human genome and other genomes. And the mission, though, of the consortium that runs it is to develop a comprehensive computational model of biological systems, and that covers so much. Early on, in the back of an envelope, when people were starting to build or model or gather data, all that magnificent, massive amounts of data about the human genome or in other genomes, people recognized that they needed to talk to one another. They needed to have a common language, or they were just going to go be talking past each other constantly. And so, folks got together and decided we're gonna kind of use a similar control vocabulary so that we're not talking past each other. And this became a hub from which there were many, many more specific spokes that emerged out of it. So gene ontology, from there you have relationships to disease ontologies, you have relationships to phenotype ontologies and whatnot. They're kind of extending or at least leveraging gene ontology work. So you have modules that emerge. Now, one of the consequences of the success in '98 was the proliferation of ontology. So the gene ontology led to so many ontologies being developed. And while it's great that we have, at least within domains, common vocabularies with semantics across multiple domains, a lot of the work that was done independently from one another. A lot of ontologies that were produced by, SMEs, subject matter experts, computer scientists, logicians. They weren't really coordinating around a common standard. And so none of these, for the most part, were developed in coordination. There was a lot of incompatibility of terms and relations. And that information silo problem that I was earlier talking about with respect to databases and inference, like data in general, just kind of manifested again at the level of ontologies themselves. So ontologies are meant to address these interoperability problems, to solve information silos, to eliminate them to the extent it can. But if you're building ontologies in an uncoordinated fashion, and you're not working together with other people in a similar domain, you're gonna likely create silos again, just ontology silos, and that is what happened. And it generated the results here in 2005, a consortium of biologists that decided to create standards for ontology development to address this problem. It's the Open Biological and Biomedical Ontologies Foundry. It still exists. And among the requirements they had, which you can see a list of over here in terms of like adding textual definitions, relations, documentation, in early days, they agreed to align to a top-level ontology to provide a starting point for all ontology development, and that was they looked around. I mean, biologists, they like their taxonomies, right? Like they were looking around. They were looking quite a few old ones. They weren't sure which one to go with. They landed on Basic Formal Ontology. Again, high level, allowed them to extend down gene ontology, like content from the gene ontology fit naturally under it, as well as many other extensions. And you see, it's today, it's still flourishing. It's the most successful, the longest living foundry effort, agreed on standards for ontology development that exists. And you can see why this is successful. Again, it's just basic software engineering principles. So BFO is analogous to Python, I think. And extensions of BFO are analogous to Python libraries. Now, you could go create code that allows you to interact with data frames or something, or you can instead start with Python and import like pandas. Similarly, you could create ontology elements that allow you to model artifacts or processes, or you could just instead start with BFO and import one of its extensions, right? It's like a hopeful starting point, a vetted starting point, so you can do work closer to the domain. You don't have to reinvent the wheel or just start from scratch. And there are many groups that took this lesson. So you see here just a lovely little diagram with BFO at the center, and you have the Industrial Ontology Foundry core. It's like manufacturing and supply chain content. You have Common Core, that's the CCO Common Core ontologies, mid-level ontology that kind of sits under BFO as well. You have a whole slew of extensions of BFO. They all kind of use basic formal ontology as a high level to govern how they model things closer to the ground by downward population. So they follow a recipe for generating definitions and meanings for terms, and they abide by the methodological principles that BFO lays down. And this is this hub and spoke strategy. So we have a hub, and then we spin off spokes. There's BFO. There's just a taxonomic representation of the Industrial Ontology Foundry's core, which I'll say a little bit about. This is operating under the auspices of the Open Applications Group, the goal being to create a suite of public and reusable reference ontologies for manufacturing. They work with government, industry, academia, and standards. They work with a lot of different organizations, because a lot of different organizations have vested interest in this content, right? They have a top level, I said. They have spokes that extend down from it, like supply chain maintenance, production, planning, and scheduling, engineering, design services. So they have domain-specific reference ontologies. They have mid-level, that's that IOF core. They have subdomains that get really close to the ground, and all of this following that modularization strategy, that hub and spoke strategy, all the way from BFO extended down to the domain and then ultimately to applications, where you actually use ontologies in programs or platforms. Here's just a little overview, just so you can see. So there's some content. If you were paying attention to that BFO class diagram, you see that on one side of the tree was the class occurrent. That's the class I'll talk a bit about later, where you find all the things that happen in existing over time. And here you have extending directly down from it, things like event or process characteristic. You have processes in BFO, you have states and planned processes in IOF, right? Like, so this is what I mean when I say extending down. So you take the base classes from BFO and you create subclass relationships or like types under those classes as you get closer and closer to the ground. You can see here on the material side, so agents and material products and raw materials, the sorts of things that you would expect to see in a manufacturing ontology. There's also the supply chain core ontology. It's also worth pointing out it's currently being developed, and so the IOF is trying to model supply chains, and so this is one of those domain-specific reference ontologies that pops down from BFO. There's all, and there it is, like scope being logistics and transportation organization, supply and service chains, facilities, traceability, inventory, and management. So, not too much, just everything under the sun. But it's a very interesting project. It's worth highlighting and exploring if you're interested in seeing how this hub and spoke strategy works on the ground from practitioners who are quite good at what they do, while also building content that might be relevant to supply chain management. So, you see they have some roles here, business processes, won't spend much time on that, just kind of giving you a flavor for the extensions. There's, of course, here, as I mentioned, the common core ontologies. This is a somewhat high-level set of ontologies that sits below BFO as well. You can see the diagram, BFO at the top, and then there's like sub-ontologies, sub-modules that sit below it, and then they have a bunch of domain stuff in that light blue. This is all hub and spoke. Again, right in that hub and spoke strategy, different modularization of different extensions, like geospatial representations, time representations, as well as agent information or watercraft stuff as we get closer to the domain. So we also adopt in this circle tracking scientific research or just good research over time, and we acknowledge that it might be fallible. So we don't think our ontologies are perfect by any stretch of the imagination. They're not perfect as they're developed by us, and they're also not perfect as we try to track the best research that we have. And so we acknowledge they may need to be changed. They are fallible in that sense. I'll give you some examples from some work that I've done. What you're looking at here is an extension ultimately of BFO. It's called the occupation ontology. The idea behind this being we needed to represent a bunch of occupation codes across the world, like US SOC, UK SOC, ESCO. They're different representations of occupations across the globe, and there are different like mappings between these, internationally. We're aiming to help support, crosswalk construction or mapping construction across these different coding structures by introducing an ontology that can kind of combine them all. But look, these things change. We recognize these things change. Here's just a snippet. 51 jobs that don't exist anymore. There's no such thing as leech collectors or knocker-uppers. Also, if you think that's just too far in the past, with the advance of AI, I'm sure you see headlines like this: 7 jobs that don't exist today but will in the next 5 years, or that don't exist today but will in the next 5 years. So we'll be changing. You're going to lose. Jobs are going to go out of existence. Jobs are going to come into existence. We have to be fallible in our representations about this. Lastly, here's adequatism. So BFO is non-reductive. Classes and relationships among them are motivated by research communities and not paraphrased away. We are not trying to come in and tell you there's a privileged way to represent the world. There's a broad, high-level, basic, logical way to represent things in the world. There's cross-heterogeneous information. There's a common formal structure. We'll find it. But we're not going to tell you that you're wrong in the way you're representing it. Now, you may come to that conclusion based on the logic that we bring down and show you, but that is a you question. We're trying to describe what you do, not prescribe what you should do. And so we are always interested in just trying to get what you're doing right, trying to get what the data says right. We're not trying to paraphrase it away or explain it away or reduce what's being done to something else more basic. So for example, in these occupation code, all this information that we're modeling with occupations, not trying to explain that, not trying to argue with subject matter experts who are supporting ESCO or Wikidata or Wikipedia that their representations are wrong, just trying to describe them, not trying to paraphrase that away. There may be differences. Like, we may disagree. Maybe baristas in ESCO. Maybe I don't think that's what baristas are. On the other hand, maybe baristas or fast food or counter workers, this is not what I think they are either. And so I disagree with US SOC. Maybe my whole team does. It doesn't matter. It's still valuable. It's still real. It's out there in the world, and we're going to model it. And that is like that's ultimately the four convictions, I think main convictions of our field right there. Main convictions of BFO, Basic Formal Ontology. Now you'll see some of these in other modeling circles, but I think for the most part they are cornerstones of what we do when we're modeling using Basic Formal Ontology. And they help us both solve, again, that interoperability piece of the puzzle. We do this by using a common top-level standard. And we also do this by following a hub-and-spoke software development strategy while trying to model the real world altogether, and acknowledging that we may be mistaken about our representations, but nevertheless trying to represent the logical space of the world as it is and as we find it. All those pieces together, all those convictions together, again, don't just help us with the interoperability, they help us address data quality problems. Why? If we're just describing as best we can the data in the broad logical structure, then that allows us to provide a logical structure, a background structure across data sets that is often implicit in the data. We are making explicit in the data what is implicit, and because of that, we can feed that into machine readable encodings that computing systems can use to identify gaps, to identify inconsistencies, can identify problems across data sets, sometimes within data sets. And those are things that we can turn back and share with users of the data. Like and say, just like this, I found this, did you mean to say it? Did you mean to represent things like that? Is this what you meant? Now, they're the experts. They're going to know. They're going to know whether that's correct or not, whether the output's correct or not. But, in my experience, very often using these methodological convictions to help guide our development, and then using that attitude of just bringing it to the SMEs, the stakeholders, the sponsors, and saying, look, I'm not trying to tell you you're wrong, but is this what you meant? That has done wonders for improving data quality. That has done wonders for helping researchers on the ground identify what might be wrong without trying to accuse them of anything. And then, it's up to them, but we have, to fix it, that is, but we have tooling, we have resources, we have standards that help us more easily identify when things might be mistaken. And that might sound somewhat trivial, but I tell you what, it is not. And if it were trivial, we wouldn't be in such high demand. So now I've told you about, yeah, let me emphasize that one more. If that were trivial, if that had been a solved problem, Google wouldn't be hiring ontologists. Amazon wouldn't be hiring ontologists. You'd think if anybody would have solved these sorts of problems, they would have, but they haven't. They still come talk to us. So, all right, with that, I'm going to move over to the theory of BFO, some of the more details about BFO now that we're fully motivated. So here's that taxonomy. This is a subclass taxonomy. So what that means is you see this thing continuant circled. It means that's the collection of all the things that are continuants in the world, and all of those are subclasses of the class entity. So anything that's a continuant is also an entity. The same for all of these other arrows. But what is a continuant, I hear you say? Well, they're things that exist in time, wholly present when they exist at all. They're entities. They lack temporal parts. They're not things that exist, as parts of time, you might think. They're things like you and me or my computer. They're in contrast to occurrence. These are things that exist over time. And there's this division between a continuance and occurrence. There are no instances in common. Nothing is both a continuant and a current. And over an occurrence, you'll see things like processes, like baking a cake or having a birthday party or your life. Among the most important logical relationships in BFO is parthood, and it comes in these two flavors, and it's kind of divided along this continuant and occurrent branches. So BFO, we have continuant parthood, and we have occurrent parthood, and this reflects the fact that continuant, that class, is closed under continuant parthood, and so is occurrent. That is to say, no continuant may have or be part of any occurrent, and no occurrent may have or be part of a continuant. If something has a continuant part, it's a continuant. If something has an occurrent part, then it's an occurrent. As I said, these classes that you're seeing, they represent collections of instances, like class of tables would fall under objects. Your dinner table would be an instance of that class table. And class A is a class B. It means just what I said a moment ago. There's this instance relation. Any instance of, say, material entity is an instance of independent continuant. But this line here is worth emphasizing because it's between types and tokens, or classes and instances, which is another way of saying the same thing. So, and here I'm going to represent types or classes up at the top, and these boxes, and then instances at the bottom. These are these things that fall in them. Like, so for an example, like, how many humans are listening to this talk right now? Do I mean instances or types, right? Like, hopefully there's just one type human, but there hopefully, if I've done my job well and this is popular enough, there are many instances listening to this as well. Independence or dependence is also an important notion at the core of the basic logic of basic formal ontology, because some continuants depend for their existence on others. So like qualities, we'll say, will depend on objects. Dependence is cashed out in terms of this notion of existence. So some things have to depend on other things to exist, and others do not depend on anything for their existence. The latter are categorized in BFO as independent continuous. They don't require anything else, or they don't depend on anything else for their existence. But the former include what we call specifically dependent and generically dependent entities, as well as processes. We're going to walk through these so you can see kind of the flowering blossom of BFO with respect to dependence. So specifically dependent continuant. These are continuants that are in every case such that they specifically depend on some independent continuant for their existence. So, for example, the mass of a tomato specifically depends on a given tomato, and the shape of your smile depends on your face, and so on. Nobody else can have that smile. It's yours. They cannot migrate across bears. So just like I said, the specific shape of your smile depends on you and cannot depend on me. It's your smile. Under specifically dependent continuant is a class of qualities, and these are qualities that inhere in independent continuants, like the redness of an apple, as you can see here. And instances where quality are said to manifest in full whenever they manifest at all. For example, when an apple bears redness as a quality, there's nothing more to the quality than the redness. And similarly, the shape of your smile on your face is there for the whole world to see whenever it's there at all. There's nothing more to the shape than what's on your face. Even so, various qualities in mind may be instances of the same subclass of the class qualities. So, and what do I mean by this? So, there's 16 kilogram class, 15 kilogram class, 14 kilogram class. Lots of instances fall under this. I just used some pictures here as instances just for illustrative effect. You see Regina, Cameron, and myself. Certain instances may fall, as I said, under different specializations of subclasses of qualities. So you might move these things around. If you say that John has a certain weight, this is 15 kilograms at one point, or 16 kilograms at one point, this instance itself may move to 15 kilograms, just like Regina's 14 kilogram instance might migrate over to a 16 kilogram instance. It can't migrate away from her. That's still going to be her instance of weight, just like my instance of weight. Like, they can't be shared by other people, but nevertheless, those instances can fall under different types. We sometimes call these determinables and determinates. So the determinables being that common class under which John has to have a weight, and the determinant being a spectrum of weights John might have, or that instance might fall under for John. Even with determinate change, though, at no point does any instance of, say, quality migrate to a new bearer. So John's weight can never be Regina's or Cameron's. They're they're just distinct instances. We'll go through this, but I'm going to pass over that. You feel free to read it at your leisure, but this is just a little philosophical stuff, and it's not official BFO, so I'll move on. In any event, realizable entities are another type of specifically dependent continuant. And here, these are dependent entities that need not fully manifest when they exist at all, such like solubility, which inheres in sodium chloride. So, attributes of some material bearer that only become manifest under certain conditions is characteristic of the class realizable entity. These are just saying realizable entities underwrite what bearers can do. So, suppose I ask you about a given portion of salt. Does this salt exhibit a lattice structure? You really just have to look at the salt to see. Now, suppose I ask you, is this portion of salt soluble in unsaturated water? You can't just look at the structure. There's something else there. There's something you have to test, something you have to put in different conditions, different circumstances to evaluate. That's the distinction. There's a lattice structure which is right there fully manifesting its quality, and it underwrites or it grounds, I'd say, what the salt can do in different circumstances. But that ability, that realizable entity, we'll say, that kind of is is what allows us linking that lattice structure to something like dissolving. That's a separate entity in its own right. That's the thing that we characterize when we talk about salts being soluble. The world is often the way the world is often differs from the way the world could be or could have been and will be, and we represent these various ways as modalities in terms of realizable entities in BFO. The yoga mat is black and you can see it, but it could support a sleeping cat without you seeing it. What grounds that? There are two special types of realizable entities worth talking about. One's dispositions. So this is again a subclass of realizables. These are realizable entities such that if they cease to exist, then their bearer is physically changed in some way. And its realization occurs when and because the bearer is in some special circumstance. It occurs in virtues of the bearer's physical makeup. So a great example is just what we've been looking at, sodium chloride. The reason sodium chloride is soluble is because of its lattice structure. And if sodium chloride loses its solubility, something about the lattice structure must have changed. There's a necessary relationship between them. We say dispositions are in this sense internally grounded, and they are in contrast to roles, which are realizable entities that exist because there's some single bearer that's in a special physical, social, or institutional circumstance where it doesn't have to be, and is not such that if it ceases to exist, the physical makeup of the bearer is changed. So a realizable entity that is a role, not necessarily fully manifesting whenever it's being held by a bearer, nevertheless, if it's lost, it need not affect the material structure of its bearer. So here's a display of a bunch of U.S. presidents. This is a role, I'll say, a role that the U.S. president role, that is, that they occupy. George Washington wasn't physically changed when he got the role of U.S. president. He wasn't physically changed necessarily when he lost the role. Same with other presidents. It's a realizable entity, though, in the sense that it gives new powers. When occupying the presidency, role gives you new powers, but nothing physically about you changes if you gain or lose it. You can just do new things. In this respect, that break between the physical basis and the abilities, that we say for roles, they are externally grounded. It's more about the combination of the bearer of the role in an institutional, social, or physical context that grounds what the bearer can do. As an example, just to highlight the inventor of Basic Formal Ontology, because he deserves all the laurels, here's a picture of Barry Smith, who is an agent, we'll say, which is a type of object, which is a type of material entity in BFO. And Barry's an instance of agent. There's also this role that he has. He's the SUNY Distinguished Professor of Philosophy and Julian Park Chair, and that is a very distinguished, very prestigious role he bears, that role being a realizable entity. And this role, this SUNY professor role, is an instance of professor role, and he bears this. There's a logical relationship between that role and what he bears, and we have to make this explicit for the machines, right? We can't just say there's a role and then there's Barry. We have to connect them explicitly. There's a special type of subclass of disposition it's worth calling attention to, called function. And these are dispositions that exist in virtue of the bearer's physical makeup, and this makeup is something the bearer possesses because it came into being either through evolution or intentional design to realize processes of a certain sort. Put another way, a realizable entity is a realizable entity if it's a disposition that exists in a bearer, and the reason the bearer exists is because or to realize whatever processes or whatever function it has. Like knives. Knives are designed to cut. They have a function. The reason they exist, the reason the material is the way it is to cut. They can do it so poorly, they can do so well. They're gradable in that respect, but ultimately knives exist to cut. That's their function. In this respect, we can say that functions are purpose-grounded rather than internal or external, although they are internally grounded because they are dispositions. Now, I've spent this time so far talking about specifically dependent dependence on independent continuants, but there's also generically dependent entities. And so they are contrasted with from specifically dependent in that they can be borne by many different things, many different bearers. They fall right here under the class of continuant, and they're meant to really capture this patterns that we see out in the world. So we're very much disposed to recognize patterns with our perceptual faculties. As you can see here, there's 6 pictures of my mom. But we see patterns all over the place, and they often lead to scientific achievements, right? Like great scientific achievements have emerged largely in part because of our perceptual faculties and our ability to recognize such patterns. Now, earlier versions of BFO didn't permit dependent entities to migrate across bearer, and this was true in current versions of BFO for many years, so your smile just being dependent on your face. But as mentioned, these traditionally and still do fall under specifically dependent continuant, but it was recognized that we needed to be able to allow for patterns that cut across bearers. And so this led to the creation of generically dependent continuants. And these are continuants that are in some sense copyable, that is patterns. And I can tell you that Barry told me once that he named this class generically dependent continuant because it's such an ugly name, nobody would confuse it with anything else. Now, you probably agree, but just to pump the intuitions here, snow is white and Schneis Weiss may be used to express numerically identical content, i.e. the same pattern, across different speakers. And that's the idea. There's something common, some semantic meaning between expressions like snow is white and Schneis Weiss that hopefully it's about white stuff on the ground, white cloudy crystals that populate on the ground. I don't know, there's a scientific way to describe it, but basically snow, and it being a certain color. So some patterns, of course, are necessarily about something and some aren't. So snow is white expresses content that presumably is about snow, but centimeter or a period, not necessarily about anything, but they're patterns nonetheless. Now, most generically dependent continuants represented in BFO extensions are patterns that are about something. For these, we call that class of things information. Information is just generically dependent continuants that are about things. And different ontology extensions extend down to talk about information, but they all use is about, which is a primitive relationship between information and some entity in the world. And that's how we make this connection. But in any event, many measures, things that you see on like measurements, units, they are about independent continuants. They are about stuff in the world in just this sense. So here's a design pattern, so a visual diagram of a representation in a Common Core ontologies that represents measurement. So an object in this case has some quality of interest, such as a length, which is measured by some information, which adheres in some bearer with an associated measurement unit and some value. And just so you can read this, is measured by as the inverse. It's a flip around, that is, of is measurement of. And you see is measurement of, just so you know, is a subproperty, a subrelationship of is about. And so we tie a nice little bow there on the information side. A more complicated example, which I think is worth going through nonetheless, is that just to note that generically dependent continuants may be about other generically dependent continuants and not necessarily about independent continuants, but although ultimately they will be, but still also about generically dependent continuants as well. And so here's a good example, I think, to highlight this. So Beethoven's Ninth Symphony is a symphony. We'll say it's an information thing, ultimately, that is concretized, we say, in some ink inscriptions. And concretized in is a relationship in BFO that links information to qualities or specifically dependent continuants that are inhering in bearers. And so in this case, you have ink inscriptions, and the ink inscriptions are what concretize Beethoven's Ninth. And now the ink inscriptions, of course, as I said, adhere in some parchment, which is a material thing. And then we say that Beethoven's Ninth then generically depends on that parchment. So there's essentially a triangle there, which we'll talk about in just a second. But also note that this is, in another sense, Beethoven's Ninth is about an orchestral plan. A plan, and this is where we link the GDCs to generically dependent continuants to other generically dependent continuants. When you make this connection of aboutness between the ninth and being a plan for other people, a plan for an orchestra to perform, And this musician plan that is like in the heads, or in a sense, or concretized in the qualities of the brains of these various individuals, or the dispositions in the brains of these various musicians, it can be realized in, like manifest in processes like a performance of Beethoven's Ninth. And altogether, then you have that Beethoven's Ninth triangle being concretized in the ink inscription that adhere in a parchment on which Beethoven's Ninth generically depends, and that ninth can be about an orchestral plan that is itself concretized in the brains of musicians that altogether, if they play and they train enough, can realize in a beautiful performance of the ninth. Now, I've mentioned in passing material entities as I was moving through these dependent things, and material entities are independent continuants. They don't depend on anything for their existence, but they're certainly an important class. Many of the examples that we just talked about fall under immaterial entity. These are just independent continuants that have matter as parts. So like you, me, apples, cars, blankets, and there's subclasses of material entity like objects, object aggregates, and fiat object parts worth discussing. We see those right here. An object is a material entity that has some kind of causal unity over it, where its instances are maximal with respect to that causal unity. So examples of causal unity include things like physical covering, like the interior of an object covered by some membrane, like a cell, as well as the internal forces like ionic bonds holding together molecules, or engineering assembly, like mechanical assembly through screws or fasteners when it's really, really tight. That can exhibit causal unity. I say really, really tight because it's important to highlight something of a rule of thumb here. So when you're trying to determine causal unity, you can think to yourself, if moving a proper part of some material entity requires moving other material parts of that entity, there's likely causal unity between them. So for example, if you grab my arm and pull me close to you, the rest of me will likely come. And there's causal unity around me, right? You pull one material part, the rest come with it. Now, an object, as said, is not just manifest causal unity, but its instances are maximal with respect to that unity. And so, to say something is maximal is to say that it is causally unified, one, by that causal unity, and that any part, or if X is part of something, and Y is causally unified in precisely the same way, then X is identical to that thing. So this is just to say there is only one causal unity binding them all. So if you're trying to identify causal unity around just my arm, you'll note that my arm is part of something larger, and there's a causal unity around that larger thing. And so there's really just that one maximal causal unity that brings us all together. You can't just pick out parts of me and say that's causally unified. For example, relative to causal unity, by covering your torso is not maximal, but the whole of you as an organism is. There are also object aggregates, and these are defined in such a way that all members of the aggregate are objects, and they don't share any parts in common. For example, you can define an object aggregate that is all the instruments in an orchestra, all the members of a band. But more generally, the X aggregate locution is intended to be a recipe that may be applied to other aggregates. So we include object aggregates, but you can have role aggregates. You can have GDC aggregates. You know, the world is your oyster, or if you like them. You can have an oyster aggregate, whatever you want. There's also fiat object parts, and so certain parts of objects are not themselves objects, but they warrant categorization beyond merely being identified as parts, such as, parts of the earth, like the north and south portions of an island. These are worthy of naming. These are worthy of taking seriously, like, Ireland, for example, and differences in the north and the south, differences in parts of these portions of a given island exist regardless of whether we delineate them so, and they kind of bona fide, in the sense, objects worth identifying and naming nonetheless. There's also, in contrast to material entity, immaterial entities, and these are immaterial, or independent continuous, I should say, that do not have material as parts. So any entity that has a material entity as part is a material entity, but material entities, I'll note, may have immaterial entities as parts. So the trunk of my car has a bunch of material stuff in it, but also there's like the space that doesn't have material stuff in it, but it's still part. You can plausibly call that combination of that space and my car, the material stuff, my car. That's okay. You can have a material entity that has an immaterial part, but you can't go the other way. So anything that has a material entity as part is a material entity. Material entity is closed under parthood in that respect. Not all independent continuants have material or matter as parts, so territorial boundaries, the internal hulls of ships or capsules, they're not identical to whatever material is associated with them. Look, an example here is an archaeologist might seek to find a site through which a contemporary river used to flow, but they're not looking for the material the river used to flow through. That's lost to time. They're not going to find the water or the sand. They're looking for something immaterial. Where was it? One of the subclasses here was identifying as continuant fiat boundaries. An immaterial entity such as no time when it is a spatial region or continuant part. I'll talk about spatial regions in a second, but no continuant part whose location is determined in relation to some material entity. So boundaries, their location is determined in relation to some material entity. Another way of looking at this is that in BFO, objects are three-dimensional, and they have two-dimensional boundaries like surfaces. And then surfaces, they intersect. When they intersect at one-dimensional boundaries, and then those we call those lines, and those lines intersect at zero-dimensional boundaries, right? But there are no three-dimensional boundaries because boundaries are always entities of some lower dimension in BFO. And X has a lower dimension. Y is a relationship. It's not in BFO proper, but it's in the background theory. It's irreflexive. This just means nothing can have a lower dimension than itself. It's asymmetric. That just means that X is a lower dimension than Y. It's not the case that Y is a lower dimension than X. And it's transitive. This means if X has a lower dimension than Y and Y has a lower dimension than Z, then X has a lower dimension than Z. And altogether here, if X is a boundary of Y, then X is a lower dimension of Y. Now, speaking of three-dimensional immaterial things, we do have sites. Now, sites are three-dimensional immaterial entities, and they have boundaries that coincide with the boundaries of one or more material entities or locations determined in relation to some material entities. So these are that three-dimensional thing. So not surfaces, not lines, not borders, not points, those immaterial phenomena that we encounter, but sites. Like the hull of a ship is three-dimensional. The space of your living room is three-dimensional when you're talking not about the material things, but just the space itself. And examples here include things like a rabbit hole, or a warren, or the interior bedroom, or the hold of a ship, or the cockpit of an aircraft. Now, these are distinct from spatial regions, which are also immaterial entities, but they're continuants that are part of spatial projection of some portion of space-time at a given time. Spatial projection is a relationship in BFO that holds between spatiotemporal regions, which are actually on the occurrence side. It's the way we bring together time and space, and a spatial region at R that is its extent. So spatial projection in BFO is exact. So if something spatially projects onto some spatial region, it doesn't project on anything smaller than that. That's it. It's exact. So now, what I've done here is I've walked through the immaterial side and the material side. I've walked through just about everything I've walked through everything on the continuant side in terms of dependence and in terms of relationships to independent continuants. But now I'm going to turn over to the other branch of BFO, that other main branch, which is the occurrence side, and that's where we'll find processes and things that exist over time. So processes, they're a subclass of occurrent, and they are also dependent. So some occurrent entities depend on continuants for their existence. So processes like the vibrations of molecules or rotations of molecules that underwrite temperature measurements, or the things being measured that are parts of the life of an apple, for example. Processes are where happenings live, and all processes in BFO have at least one temporal part and are such that some material entity has to participate in them. Where participates in is a relationship connecting specifically, generically, and independently continuant, independent continuants to processes. So it's a rather broad relationship. And a given process may have realizations of some realizable entity which inheres in some independent continuant. And what I'm going to do now is I'm going to walk you through this chain here. So you have processes. They can be realized by realizable entities like dispositions of salt to dissolve, right? Solubility is a realizable entity, but dissolving is a process. And solubility is realized, we say, when dissolving is occurring. And so this is how we make that connection. Realizable entities, of course, inhere in independent continuants which is how we have this chain from processes through realizables all the way to independent continuants. Now, processes, there's a special one to identify, a special class under here, which is a history, which is the sum total of all processes associated with a given material entity. And every instance of a history corresponds to one and only one material entity. So my life is mine and your life is yours. And these are histories that we have, and that's just the sum total of all processes that we participate in over the course of our lives. Now, in BFO, we also allow for representing change, because change is quite important. It happens all the time. And if we're going to get involved with occurrents and processes, we ought to be able to represent things that change. And so instances of material entities, I'll note, have matter as parts, gain or lose qualities or parts, or occupy different locations. They move, right, over the course of their history. An apple in an orchard ripens, reddens, and sweetens before spoiling, developing blotches, and so on in a fruit basket on my island because my wife buys too much fruit. An intuitive understanding of change, then, is the gain or loss of specifically dependent continuants, qualities, realizables, and stuff. But in BFO, occurrents do not bear specifically dependent continuants, and so strictly speaking, cannot gain or lose them. As a consequence, characterizing in BFO things like increasing velocity of a vehicle or the changing direction of an airplane or the lowered volume of an alarm, they're not understood in terms of properties of processes. Lowering the volume doesn't have a property. A turbulent flight isn't, or a flight trajectory isn't turbulent in a sense that it bears a property of turbulence. So we don't say that in BFO, because in BFO, processes aren't the sorts of things that change. They are changes. They don't change, they are changes. So for example, participants do change though, but the process doesn't. So a flower, this is from a case study paper in Applied Ontology for Basic Formal Ontology. As part of a suite of upper level modeling cases that our team developed and published in concert with a whole bunch of other top level ontology models. So in this case, a flower is red in the summer, and as time passes, it changes to a different color. This case is supposed to represent how change can occur. So, and here is our design pattern, a petal changing color in this case. So we had an instance that was a color of red at some time. It was a color. There was an instance that fell under red and then fell under brown. There was temporal relationships over time and blah, blah, and all that good stuff. And then there was a flower that was participating in some process of withering, and that flower bore the color. The flower participates, as I said, participates in a withering process. And the participant can change. It's just that the process of withering can't. So it's the participants that do the changing. And whether that means that color instance moves from one class to another, from red to brown as a type, or whether the flower loses other properties or parts as it's withering. It bears nevertheless an instance of red over one interval and brown over another. Remember that determinates determinables distinction I drew. Now, I've already mentioned spatiotemporal region in passing while I was talking about spatial regions, so we should probably hop in there because it's certainly relevant to change over time. So the history of a material entity, as I said, always one in one with a material entity. It occupies some spatiotemporal region, and that is an occurrent part of what we call some instance of space-time. And spatiotemporal regions have both spatial and temporal extents. So an apple, say, could occupy a spatial region, or in the history of that apple can occupy a temporal region T. In the history of that apple occupies a temporal region, or spatiotemporal region S, where S spatially projects into that spatial region and temporally projects into that time. You see, spatial region, spatial projection. So remember, spatial temporal regions are the sorts of things that are useful and described in terms of spatial regions, which makes spatial regions quite useful for our purposes. It's sort of like spatiotemporal regions are how we bridge that continuous spatial region class, where space is, with the temporal region on the occurrence side, which we'll talk about in a second. I did say temporal regions, right? So they're right there, and we need them to tie a nice little bow around all this. So in BFO, we don't distinguish between processes and events. But we do have processes of baking, apple, pie, and they have proper parts such as cutting and blah, 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 like that. And proper process parts may be further divided in, say, cutting of specific apples. And what we have here are boundaries, and we have temporal regions underwriting it, because this is where all this stuff happens. And then, but in these temporal regions, we want to draw a distinction between points and intervals. and we do just that. And so below those we have zero-dimensional temporal regions, which is again where there's temporal projection for occurrence into a single point, and then we have one-dimensional temporal regions where there's temporal projection from occurrence spatiotemporal regions into an interval. Now, process boundaries, these are boundaries between processes that have no temporal parts. They're just kind of the cutoffs between processes, so the beginnings and the ends. Those project onto zero-dimensional temporal regions, while the longer processes, the things that the process boundaries abut, those project onto temporal intervals. Well, spatiotemporal relationships, there are entities, as I said, they are located at spatial regions, and then entities that exist at temporal regions. And so far I was talking about the spatial projection, temporal projection. Those were very exact, so there's no subpart on the projection relationship. It's shrink-wrapped in a sense. Entities, though, and entities that are located at spatial regions or exist at temporal regions, they're what we say are partial. So if X is located at R, then X is located at least R. It could be more than R, right? Like, similarly, if X exists at a time, then X exists at least at time, but it could exist at a longer time. So again, not like the projection relationships, which are exact. As I said, there's also the processes occupying spatiotemporal regions, and then spatiotemporal regions projecting on space and time, as I said. These are exact. So there's this occupancy relationship. So if P occupies temporal region T, then P occupies just T. And if S, a spatiotemporal region, projects on a temporal region, then it just projects on the temporal region. Same for a spatial region. And here's a pretty diagram that kind of shows some of these relationships. I won't walk through that, but it is yours to ponder over and understand at your leisure. Now, that was the theory of BFO. Now I want you to see a bit how to actually do some building with BFO, and this will be the last thing we cover. And we do this, I'll say, by starting through competency questions. Now, competency questions are used to guide ontology development in general. It's not something the BFO community invented. And what we do is we first identify a list of questions that we want to be able to answer with ontologies. This helps us scope our project. Here's some examples of competency questions from Maria Keed and Zane, and on the roles of competency questions in ontology engineering. You can categorize competency questions of different sorts based on their types. So like, is Ruby a type of chocolate? What is the base of thin and crispy pizza? What's the domain and range of the eating relationship? So the different kind of competency questions that you might want your ontology to be able to answer, and questions that it should be able to answer, and will spur off other questions as you explore the domain that you're representing with the ontology. And so I'm going to walk you through an example of how to build an ontology using competency questions, and I'm just going to use this one. At what speed does a patrol boat move in knots over an hour? So what we need to do here is, if we're thinking about building something like this out of basic formal ontology and some of its extensions, we'll need to identify the classes and relationships relevant to this question. Here is BFO. On the left, this is taxonomy that we kind of walked through, and on the right you'll see a bunch of relationships that connect parts of the taxonomy to other parts. You've seen some of these. I talked about concretization, located in, I talked about participates in. Some of them I didn't talk about so much, but there aren't that many, but they're all used to link parts of the class structure to other parts of the class structure. And so, but I don't want you to get confused. I want you to have a bit of a recipe when you're engaging with modeling with BFO. And so when you're identifying classes, here's what I want you to do. Follow this recipe. Start with material entities. Identify those. Then move to qualities. Then what realizable entities, i.e. what the things can do that you've identified as material entities. Then what they actually do. And then where those things live and where their boundaries are located. And then when they exist. And then last but not least, information that might come up in a competency question about everything in 1 through 6. And I save that for last because it is very common that people confuse information for what it's about. So if you've already modeled everything before then, it's hard to confuse information for what it's about, because information will be the last thing. So follow the recipe and you won't go wrong, or at least you'll less likely go wrong. So we're looking at our example. At what speed does a patrol boat move in knots over an hour? We start with the material entities, and here we go. Patrol boat, that's a thing that has material parts. Now processes next. active motion seems to be involved, and you'll probably note that I didn't use quality. I skipped over qualities because I don't see any qualities really in the competency question. So if I don't see it in the competency question is being used to generate my modeling here, I'm just going to skip that for right now. Now I did get to this one though, speed. Speed could be a process, it could be information about a process. I put a question mark here because it's ambiguous and I'm not sure what. I want you to follow my guidance here. If you get ambiguity like this, just put an asterisk and move on. You'll come back, but put an asterisk and move on. I know you won't. I know you'll get tripped up and argue about this or think about it a lot, but I really encourage you to just put an asterisk and move on, because if you don't, you'll see ambiguity all over the place and you'll never finish the list. Don't worry, we'll come back. So asterisk and move on. Knots, measurements. I think knots are a measurement. It's information. It's about stuff. Also, hours. We have hours here, and that's another ambiguous one. Is it time? Is it the time out there? Is it a measurement of time? Now, note what I did just now. I walked through this competency question, and I walked through this recipe, and I just fleshed out the things on the list. Easy peasy. Now, we got to disambiguate. Logic is demanding. Our basic logic is demanding. We want to make it complete, and we want to make explicit all that implicit semantics that we see in competency questions and otherwise, so we need to disambiguate our structure. Now, we saw two ambiguities. Let's revisit. We can use this, what I've written here, as kind of guidance. So information is not the same thing as what it's about. So occupation codes versus the holder of an occupation. People confuse this all the time. Don't make that confusion. Information is distinct from what it's about. Geospatial coordinates are not the world. They're about them, presumably. Material versus immaterial things. Disambiguate here. Given river versus the site where it flowed. Or the bearing of properties versus the bearer. So an apple's redness versus the apple. As well as processes versus product, like baking of a cake versus the cake. Keep this in mind, and these kind of distinctions are embedded at the heart of BFO. BFO draws these distinctions, and so we avoid confusion, avoid conflation and ambiguity when we're following the structure. So revisiting the ambiguity that we came out of our competency question modeling, we see that speed could be interpreted as a process or an information about a process. So you can think of it as a magnitude of change in position over time. This is something you'd see in a physics textbook, for example. You can also think of it as the changing of position over time, which might be a process. Arbiter here, which do we care about for the competency question? That's a question for you. Same with hours. Now, I did a little of this work for you. I want you to think about the hours. I'll let you think about that. But really, the idea is, which of these representations of hours did you need to model the competency question? Now, I took a stand here. I took a stand for the sake of argument, both on speed and hours, and I'm going to model process or speed as a process and hours as a temporal region. Now, once I've done that, what I want you to do is once you've done that, mark off things or categories and interpretations off the list that you didn't use or don't need. And I want you to do that for the sake of cognitive load. Simplify the list down to this, and now you reflect on the relationships among the listed entities. For example, relationships between qualities and material entities. In BFO, we have inheres in that connects them. Realizable entities to material entities. Inheres in or has material base, depending on whether you're talking about dispositions or not. Processes are related to material entities through participates in, and then realizable entities are related to processes through realizations. Immaterial location of material entities is connected through located in, and things exist through exist at or potentially data type properties. And then whenever any such entities carry information, we have things like generically depends on to make that connection clear. You walk through this list just like you did with the classes and what you do is you tease out the relationships among this simplified list. So again, remember I said the classes in BFO are connected through these object properties, through these relationships, and the relationships that bring together all aspects of the taxonomy. And so if you have something that falls in the taxonomy, there's some relationship there that you need to fill in. Patrol boats participate in processes. That's part of the competency question. And so you should assert that participation relationship there and do the same for speed, hours, knots, measurement, all the connections that you can by leveraging these relationships in BFO. Ultimately, once you do this, you can construct something of what we call a design pattern, a visual representation of the competency question. The Common Core Ontology's design pattern right here, is born straight out of their documentation, represents a patrol boat traveling 12 knots over 1.5 hours. And you can see it's a patrol boat or ship that participates in an active motion occurring on a temporal region, and it has a speed. Now, I hear you wondering, how, John? How would I use this in a real-world application? This is all well and good, but I need to see where the rubber meets the road. I'm glad you thought of that, to ask that. Let me show you another competency question. Has a drone crossed the U.S. border? And you see some different ways in which a drone can cross the U.S. border. It can go straight across, it can fly up and elevate, or it can like meander and whatnot. Right. You might have a real-time application set up that monitors real-time drone activity, helps support decisions making, but you also might involve in this an ontology with already some conversion or data enrichment processes that go on, and this is where sort of where we meet up with that actual data in the real world. So if we're just looking at the drone activity, you might get sample sensor data that looks something like this, kind of a mess. And then you might have a representation that can help make some explicit some of the implicit semantics in that data. So for example, when we want to address this competency question with data like that, we have to think about how that data is relevant to the question and how we can model it. So just off the cuff, we might need representations of things like borders and boundaries, geographic regions, drones and speeds, lats and longs and outs and time. And I won't go through all the modeling that went into building this design pattern, but you can see what we have is we want to represent a drone participating in some process with a speed. That process occupies a spatiotemporal region that has parts like spatiotemporal part 1 or 2. The spatiotemporal parts themselves have geographic extents and interval extents, because remember, spatiotemporal regions project onto space and time. So you might have a geographic part and then a temporal interval part. Those temporal interval parts will have dates, and those geographic parts, as parts of space, are going to have decimal value, lats, longs, and altitudes. And so what I've done is I've represented different stopping points, different parts of the overall process of a drone moving through the world with different lats, longs, and altitudes, and over different dates and times. And this information can help inform our graph structures, but we have to convert the data or enrich the data that we get in a real-time drone activity with the ontology to make this happen. And this can be done with some various scripting, like RDF-lib conversion scripts. So you can take this data, and if you've encoded the ontology in the RDF-lib correctly, then you can take this data in real time and generate the ontological structure that you'd need. And it looks something like what you have over here on the right. You have a bunch of instances, and you'd have some motion process, a geographic point, and whatnot. I'm gonna you can see here there's a bit of coding involved. You may or may not get comfortable with it. I hope you do. But there's sensor data that can be converted to a CSV format. You represent the classes and instances and relations in a given ontology using its IRIs for terms like new drones identified by sensor will be represented with new encodings, new IRIs, or new names. Same with new flight paths of the drone representing by new names. You can also identify unique IRIs or generate unique like identifiers for this content that comes through in a real-time pipeline by prepending with specific, something. I use HTTPS example.com but a GUID generator here, so you don't run out of notation, right? So all this you should be able to see directly here, lats and longs being pulled straight out of say an XSD file or CSV file that matches directly up with the sensor data you're seeing right there. And so what you see at the top is the encoding in RDF-lib that will spit out ontological representations of what you're seeing in the bottom here of the real sensor data. You can also see there's conversion script that reflects more of this ontological structure, but basically what I'm trying to show you here is if you're inputting the sensor data in your code, you're using a language like RDF-lib, which is designed to help you represent ontological relationships in code and in a sense make ontologies executable. You could turn it towards CSV or other data or sensor data in this case and have it generate the structure, the graphical structure that you need to run through reasoning systems or query against. And that's where we're headed next. We're recording enriched data. So here's the sort of data that you'd see. It's on RDF. If you were looking at it through Protege, you could like open a file that looks like what you see on the right in Protege, and you see a relationship, that kind of connection between the design patterns on the left and what you'd see in Protege on the right. And then this is the sort of thing that you can run queries against using languages like SPARQL, which we'll talk much more about later, and you can encode the question, the competency question. Has a drone crossed the U.S.-Mexico border in SPARQL? It might look a little messy given the structure and all the complexity, but that's okay. Once updated with sensor data in valid format, this query can return information like the following. It talk about when things cross and when they don't cross, perhaps even, or certainly give you alerts or output when you need to pay attention to a certain part of the border. So if a drone crosses the Israel-Mexico border and an ontology updated with this information, it can queried or triggered to query it to confirm this fact. And moreover, differences in altitude, latitude, and longitude can also be queried to track flight paths, because different drones, like sometimes nefarious drones, cross paths over the border in different ways than what you would be doing if you were just flying for fun. Now, what am I saying? What have I been saying? We make explicit the implicit semantics in data sets, and it's in the interest of addressing interoperability challenges and improving data quality via general and targeted reasoning. We basically make that structure machine readable so that we can leverage tools to help us identify data quality issues and answer questions that we might need answered. Now, I'm also going to include a video here for you, because I want you to see how I want you to understand the pain involved in what I've just walked through, as easy as I've tried to make it. I'm going to give you some exercises on how to build ontological structures. You see in the projects here, that could ultimately be used to develop competency questions, but it's going to be hard going because the world is quite complicated, and ultimately I want this to motivate you, helping me and the rest of the community find a way to automate what we just walked through. Thanks.